Right, so this little Doppler simulation spreadsheet, Doppler simulation spreadsheet that I was messing about with. It might just help to visualize some of what's going on. I'll just quickly show you how it works, and then you can mess about with it yourself. You can download it from the page if you want to. So what I've tried to simulate here is a source of a noise, a source of a sound. So it's a police car with a siren that's blaring from the top. And this is the waves that are moving across. The person on the motorbike here is supposed to be the observer. And at the moment I've got both of them with their speeds set at 0, so they're not moving, although my little picture shows that they're moving. You can set the speeds here by dragging the slider left and right. Now what I've taken in here is I've taken as right is positive. I think this is more closely to the way the notes does the calculations. So if you take the slider and drag it to the right, then you'll see that the speed there increases, and I've done it in meters per second, and that means the car's moving to the right. If you drag it beyond to the left, you'll see the speed becomes negative, and so the car's actually moving backwards. But we'll just start with it on 0 for now. I've got the observer also on 0. I've set the wave speed at 400. Actually, we can set it to 330 because that's the most often quoted speed of sound. You can change those values if you want to. And I took the 2000 Hertz. It's an average frequency of a siren, apparently, according to Google. So that's where I got those values from. What I've done here is I've set up the equation, and it reads the values from these boxes. Okay, so there's the equation as it is on the spreadsheet, and I've put in a few if and then statements. If you want to see how these work, by the way, just click on them, and the formulas are up here. You can maybe learn a little bit of very simple formulas or programming. It's not programming really, but anyway, if you want to learn how they work, the formulas are there. You can have a look. So I've made some things here. So these values read from here, and so you can see in this case, as the velocities are both 0, so they're both standing still, these values are both 0, and so the ratio of the speed factors, which you multiply by the original source velocity, it's just going to be 1, and so your observed frequency is now exactly the same as your source frequency, and that's what you would expect if nobody's moving. However, we know, if you've watched all the other PowerPoints and things and videos, that if these things are moving towards each other, then this value should increase. So now if we go back here and we take the police car, and let's say for the start our observer is standing still and the police car is moving towards them. So give the police car some kind of a positive velocity. You can see straight away this formula has changed. Here we've got a minus sign on the bottom because the source velocity needs to increase this fraction. And to increase this fraction with a factor at the bottom, you have to make the bottom smaller. So that's turned to a minus. You're minusing the speed of the source, which gives you an increased observed velocity, which we know is the correct thing. Now what I did just to mess about is I made the box go blue if the frequency is increased, so it's kind of a blue shift. If you're not sure what that means, go and have a look at the applications video. Actually, I think this statement only applies to one scenario, so I'm going to take it out. If it's not taken out on your copy, then just delete it. So that's what happens if the source is moving towards the observer. Now the observer is standing still. Let's say the observer now suddenly hears the police car after them, and so this observer is a bit naughty, so she decides to run away. As she speeds up, you can see the value of the observed frequency begins to decrease. Okay, because now the rate at which they're coming together is slower, and so the increase in frequency is a little bit less than it would have been. If she actually gets to the same velocity as the car, what do you think is going to happen? Well, she goes back to exactly what it should be. If they're moving at the same velocities, their relative velocity is 0, and so she will hear the same frequency as the one that's been emitted by the siren. If, of course, she starts going faster, now the distance between them is increasing, so effectively the police car is going away from her backwards, or she's going away from it, so the distance between them is increasing. And now what happens is the frequency drops below the original frequency, and you see I've colored the box a little bit red to give it a sort of a red shift. And this works very nicely. So you can do that either way. If she were to slow down back to 0, you can see this thing increases again. Obviously, if she starts going backwards, then this is going to increase even more. If this police car was to go back to 0, if he was to stop and she was coming towards him, so now her velocity is negative, you can see the value, the observed frequency is still higher, as it should be. Also note that if the velocity of one of these people stays constant, then the frequency that is changed, in this case it's increased, is increased, but it stays constant. However, if this person was speeding up, then that increases. Or if she was slowing down, then that decreases. So you get an increase in or a change in the observed frequency if one of these is moving. But if their movement is constant, then the change frequency is constant. If their movement is not constant, if they speed up. So for example, if the police car was speeding up coming towards her, you can see there's the frequency increased. If this guy carries on speeding up, you see that as he speeds up, this frequency increases. So that's a little question that often comes up in exam papers, which you can use. So you can play with this yourself if you want to. I'm not going to go through the next sheet. If you click on the next sheet, it's pretty much the same, but here I've made it so that you can also change the wave speed just for fun. And I've asked you a couple of little interesting questions. This one is quite interesting for you to think about. Try and think about the question. If you can't figure out the answer, then you can move either of those boxes, and I've tried to explain the answer there. If that doesn't make sense, then give me a shout. But this spreadsheet works pretty much the same as the other one. Also notice I don't think I pointed this out, but obviously let's just look at the source velocity here. If the source velocity increases towards the observer, then this is a minus. You minus this on the bottom. Obviously, if that decreases, if he starts going backwards, then this has to become a plus, because now his velocity must reduce the observed frequency. And to reduce the observed frequency with this fraction, you have to increase the bottom. So those you need to notice that, and the same happens with the observer. If she's moving away, then her speed must decrease the frequency, so that's a minus. If she starts moving to the left towards him, as soon as she goes past 0, you'll see that turns to a plus, goes from a minus to a plus. Okay, so if they're both moving in the same direction, if both their velocities are negative, then both of these need to be pluses. If they're both positive velocities, if they're both moving in the same direction, then these two both need to be minuses. You can either learn that just out of your head, or you can figure it out if you understand it. Alright, hope that helps. That's the end of that. Cheerio.